As the next speaker, we have Gauri Joshi. She is a professor at Carnegie Mellon University. She works on optimization, distributed learning, and today she will talk about federated learning in the generative AI era.
Thank you. Thank you for the introduction and for inviting me to the workshop. So today I'm going to talk about federated learning in the generative AI era, as the title says. And this work, everything that I'm going to present is joint work with many students and collaborators who are pictured here. So going back to my title slide, we should think about it not just as one era, but rather many eras since generative AI models have become popular. So we can even think about it as like a generative AI eras tour, where there have been several generations of models in just the past few years. So if you go back to, say, 2014 to 2017, there was a sequence and attention era, then there was transformer pre-LLM era, and then LLM era. And most recently, we have agents and reasoning models. So if we follow the trends as we have progressed through these eras, one of the trends is that the number of parameters in these models has grown exponentially. So the latest models are more than 1 trillion parameters. And at the same time, the training data that is used to train these models has also grown a lot. So this is just an approximate range of the number of tokens that are used to train the latest models. But what has been observed in the past year or so, one example is Ilya's talk from NeurIPS in 2024, is that compute is growing, but data is not growing because the frontier models have already assimilated most of the publicly available data on the internet. So there's not much public data available to train these models on. So what we really need to move forward is to leverage new sources of data, going beyond publicly available data. And these new sources of data can be used to pre-train, fine-tune, and deploy the next generation of models. So that is where I believe federated learning plays an important role because there is a lot of rich and untapped data that is available on the edge. So edge not just includes mobile devices, but also data that is there in enterprise data silos. And a large fraction of data is generated in these edge or silos. So the question that we should ask is, can we leverage this data despite the privacy and communication constraints that come with the data being on the edge? And the answer is just federated learning. So you can use the untapped edge data together with computing advances in the hardware that is available at the edge to train or at least fine-tune or post-train models. And doing federated learning on the edge data gives benefits such as less risk of data leakage, better personalization, and access to more diverse data. So this is how I think federated learning has a place in the generative AI era. And in the talk, I'm going to talk about how it fits in some of the stages of the pipeline of training frontier models. So as you all know, there's pre-training of these models, then there's fine-tuning and post-training. Then there's some pre-inference optimization, which you can think of like before deploying the models at service time, what can you do to set them up? And then at inference time, there can be several optimizations that can be done. So yesterday, Zach and Ahmed and others talked about how federated learning methods can be applied in pre-training, like the DeLoco method. In my talk, I'm going to focus on these 3 stages, and I'll briefly talk about some works related to each of them on how federated learning can be applied to these stages. So that's the plan. Let's start with talking about fine-tuning and post-training. So we have this standard federated learning setup, which I'm not going to talk about too much since everybody here probably knows about it. The main thing that to note in this standard Fed averaging setup is that what you're exchanging is the model parameters. And current models have just too many parameters. They have billions of parameters, so it's not feasible to exchange model parameters or gradient updates naively. So how do you perform fine-tuning or aggregation of such larger models? And one of the possible solutions is to use some parameter-efficient fine-tuning methods, such as LoRA. So LoRA you might have heard of. It's this method which is very popular for fine-tuning models in a centralized setting, where you have LLMs with billions of parameters that are pre-trained. But instead of fine-tuning all of the parameters to leverage edge data or domain-specific data, what you can do is we start off with the pre-trained model, which is denoted there by W0, and then the updates that we make to the model during fine-tuning, which are the delta W, are approximated by a product of two matrices B and A, where B and A are low-rank matrices of those dimensions. And the main advantage of this is that if you compare the sizes of delta W and the B and the A, the number of trainable parameters is reduced drastically. So for instance, if the delta W was like 1,000 cross 1,000 with the R of something like 4, the total number of parameters here would be like 8,000. So it would be almost like a 100-fold reduction in the number of trainable parameters. So LoRA methods are very popular for fine-tuning models, but they have not been used as much in the federated or distributed setting. And there are some challenges due to which it is not easy to just directly apply these methods. So I'll talk about some of those challenges and see how we can address them. One of the challenges is that if you just naively use LoRA in the federated setting, there's an issue of inexact aggregation. So what that means is that suppose I have these 3 clients and each of them train LoRA modules, starting from the common pre-trained model. Because of data heterogeneity, these matrices are different from each other. And when you aggregate them, what we want to do is reconstruct the delta W, which is the average of these local updates. So the right thing to do would be to take the products of these matrices. So each would represent the local updates of each client, and then take an average of them to get the global update and apply it to our model. But the problem comes when you go to the next round. So this delta W now needs to be sent back to the clients for the next round, and this is too expensive because this is a D cross D matrix. So we want to be efficient in terms of communication and avoid this cost. That is why what is often done in practice, as proposed by this paper and used in many other recent works on federated LoRA, is that you have these matrices. When we average them at the server, we just average the B's and average the A's separately. And then you get the B bar and A bar and just send these back to the clients. And this is not as expensive to communicate because these are low-rank matrices. But as you can see, the problem with this is that what we should have done is that, the average of the products, and what we are doing is the product of the averages. So it doesn't match just by linear algebra. And then as a result, when the clients start the next round of training, their local model effectively will be this one, which does not match with what it should be. And this mismatch is much more prevalent when there's higher data heterogeneity across the clients. So what we need is low-rank methods that do not have this inexact aggregation problem. So that is one issue. Another issue with applying LoRA methods in federated settings is that the clients can have computational heterogeneity. So some clients might be able to train more parameters than others. So one way around it is that you can consider different ranks of these LoRA modules at different clients. But how do you aggregate them? So one method of aggregation is to zero pad these matrices and then average them as B bar and A bar and send them back after some truncation to the appropriate sizes. This method is one of the proposed methods, but as you can see, the zero padding can introduce some errors here. So another approach is to take the products of them and average the products, and then when we get the delta W matrix, because we don't want to communicate this big matrix back, we can take an SVD and find different numbers of singular vectors according to the constraints of these devices and send them back. So both of these methods are possible, but the issue is that both of them can lead to some accuracy loss because you're losing some information when you're either zero padding or doing SVD. Another challenge is that the whole idea of LoRa is based on the hypothesis that this delta W has some low intrinsic dimension. And that is often true in many applications in a centralized setting, but in a federated setting, that may not be really true. And that is because you have all of these local delta Ws, and we are averaging them. So the delta W that we get globally may not have as low of a rank as we would want. So if you look at the actual rank of delta W in a federated setting, it's not very low. So we did some experiments to study this. So these are the singular values of delta W. So this is just full fine-tuning, no LoRa. And then we are comparing them for the centralized setting and then federated with IID clients and federated with non-IID clients. And these are just plotting the top 64 singular values. So that's why there's this cutoff here. So what I want you to observe here is really the trend. So if you go from left to right in these plots, there's this upward trend when you go from centralized to federated IID to federated non-IID. So the intrinsic rank of delta W is increasing as you go to more heterogeneous settings. Yeah.
Two questions. So the method where you just send the first few singular values of delta W, where you average it correctly, does that perform worse than this B bar A bar method?
I have some results later which show the comparisons. I don't remember off the top of my head.
On this slide, what is the method? Is it the B bar A bar method or is it the...
This slide, you are not doing LoRa. I'm just doing full fine-tuning and then analyzing the singular values of delta W. So this is without approximation. So what we want to see is a low rank approximation, a good approximation of delta W.
Still doing low rank on every server?
No, so in this plot, we are just analyzing delta W with full fine tuning at each client. No low rank approximation.
What is FL with what are the FL baselines then?
FL baselines are where your data is distributed and you're doing full fine tuning at each of the clients and then averaging them.
Just one step of averaging?
Yeah, just one step of averaging and then analyzing.
I see, but with one step of averaging, you're never really aligning the clients to find a shared subspace, right? So is it surprising then that the rank goes up?
Okay. So I don't remember at which stage exactly, after how many rounds this is measured, but I think the message here is that because of heterogeneity, the rank kind of goes up.
But it's still B bar A bar method.
No, so this is not LoRa, as I said. Like this is, yeah.
Okay. Kind of.
So
Okay.
the rank goes up compared to what baseline? I guess what's
compared to,
baseline?
so you're comparing them relatively with each other. So this is centralized where all the data is local. This is where it is decentralized.
Okay.
So it's just like a relative comparison. Yeah.
What kind of a heterogeneity you have here? What kind of tasks?
Okay. So this is like heterogeneity is generated using the Dirichlet distribution, like what is run typically.
So it's what data set is this?
I think this is one of the image data sets. I don't remember. Yeah.
So image classification.
Yeah. But we have later some experiments both for image and language data sets, yeah. Okay, that's good, yes.
So I just want to ask about what is the computation performed in each local client. They first compute the full rank update, then decompose that as two low rank matrix, or they directly update the low rank matrix.
So in the LoRa methods, you directly update only the low rank matrices, B and A. So you start off with the pre-trained model, you do forward pass through the pre-trained model, and then update the B and A matrix parameters. Yes.
Sorry, so before, I know that you are no longer doing low rank, but before we move on further from there, so I'm trying to understand why don't I look for a low rank matrix that is sort of like the berry center between all the low rank matrices used by the devices. I mean, like in the standard situation, like non-low rank situation, right, we use the average because it sort of minimizes the L2 distances summed up. But of course, you can I guess one can formulate a similar problem. It's just you look for a low rank matrix that minimizes some, I don't know, Euclidean or geodesic distance from all the other low rank matrices, and I believe that actually this problem can be efficiently solved.
Yeah, that's an interesting idea. I think people just go with the simplest solution, which is the average, but there can be better ways of averaging these matrices. Like one thing to keep in mind is that like whatever method we can come up with, it shouldn't look at the data at those clients. So it should be somehow agnostic to looking at the data distributions, and like if the method can be designed in that way, it would be a good candidate. Yeah.
I just have a comment backing up I think what you're getting across on the slide, and that is because the nature of LoRa, it can look in the abstract like it's sort of a simple linear, something that's linearly decomposable. But when it gets attached to the LLM, it attaches at every layer.
Yes,
so it
right.
has this interaction through nonlinear layers, and so when you take a singular value, like if you restrict to like just a finite set of singular values, you're in some sense you're breaking an assumption that the next layer has on how many. Almost like what the channel of information is. So I guess all I'll say is everything you're observing here, I've seen in practice as well, in that like it gets very complicated as you average similar values or anything that's sort of like, because there's assumptions between layers of how the LoRa's interact that you learn in concert.
Right. Yeah, thank you for the comment. So as Sean said, these LoRa matrices, they are used, are typically applied for attention matrices, and then they are applied at each layer of the transformer. So there's also some non-linearities in between that come up. So this is the third challenge. So what we really need is a higher ranked approximation. So the way we fix these challenges, let me just talk about some of the approaches that we can take. So the first thing, let's go back to the inexact aggregation issue where we had this pair of matrices, and the number of trainable parameters here is 2 times R times D. And the issue is that these two don't match. So one way to address this is to change the format of the LoRa module a little bit. So what if we change it to something like this, where you have the B and A matrices, but those are now frozen. So they can be initialized as like Gaussian random variables. Anything reasonable that makes them full rank works here. And then what we have is just a one single trainable matrix, which is H, which is this square matrix in between. And here now the number of trainable parameters still stays n equal to 2RD, but the inexact aggregation issue just goes away naturally because you only have one matrix to average. So when we average these locally trained LoRa modules, the B and the A are frozen across all of the clients, and you're only averaging H. So there's no mismatch issue here. Okay. So that's an easy way of addressing the first problem. It turns out that this module, this BHA version of it, also addresses the insufficient rank problem to some extent. So if you look at the maximum effective rank that we can get from each of these, on the left-hand side, the regular LoRa module, the maximum effective rank is just R for that product. But here, the maximum effective rank is square root 2RD, that's the size of that square matrix. So we can increase the maximum effective rank. So note that D is much larger here than R. So we can increase the maximum effective rank while keeping the number of trainable parameters the same. Okay. So this is good, but can we further increase the rank with the same number of trainable parameters? So that is where we introduce this idea of using multiple such heads instead of one. So we have this module, but now we use many of them. So I'll start with this one, but now instead I will use several of them in parallel and then add up all of them to get the delta W. Yes?
Question. You're freezing A and B. Do you do some initial train? I think the vanilla LoRA algorithm initializes A randomly and B to 0, so that like if by default it's adding nothing.
Right.
Do you do something to get that non-zero?
No, so here we just initialize with Gaussian random variables.
We initialize both Gaussian.
Both are Gaussian. Yeah. Because the form is a bit different, there's a H in between.
Yeah.
We don't need to do that zero initialization like we had before.
I'm a bit confused as to, so you have the H now that has order RD parameters. What were we competing against? I thought we were trying not to send too many parameters across.
So we are competing against just the regular LoRa module, which has, again, the same number of parameters. So I'm keeping the number of parameters same, but I'm trying to increase the effective rank of the delta W.
So the original, so as opposed to, let's say we didn't have the low rank, what is the number of parameters?
D square, yeah.
Okay, so I see.
So basically for the same number of parameters, the composition should be more expressive?
Yes,
Okay.
right, that's the idea. And then if you go to this multi-headed version, which is why we called it Ravan, there's the Indian mythological figure who has multiple heads called Ravan, yeah. Sorry? Sorry, I didn't hear you.
D square, not 2DR.
Oh, D square, I think he asked if you don't use LoRa.
Okay, but just the LoRa adapter.
LoRa adapter is 2DR, yes.
This is then more parameters then, right?
No, so this is the same number of parameters because I changed the size of this matrix to keep the number of parameters the same.
Okay, so no D square, but 2DR, and it's the same. Okay.
Yeah.
Got it.
These B4 agents, are they all updating their like fine-tuning directions in a like on a low dimension space? Because originally they can like update into different directions, and now you fix B, which is of the low dimension.
I see. Yeah, so there is some constraint that gets introduced when you freeze A and B. You are updating in a lower dimensional space, that's true. But the thing is that because you get higher effective rank, it's still a more expressive update.
So BI actually are different for agents?
In the left-hand side, you have all of these at each client. So they are same across clients. So B and A in this case will be same across clients, and you'd only be averaging H because these are the only ones that are trained.
Yeah, so the updates are actually constrained in the like same space for all agents.
Yeah. Right. So what we propose is you have many of these heads, and then you can notice that I reduce the dimension of each of them such that, again, the number of trainable parameters stays 2RD. It's a little bit more than 2RD because we also have some scalar parameters that we multiply for each of them and then train those. But that is insignificant compared to the 2RD. But it turns out that the maximum effective rank of this now becomes square root 2RDH. So we are increasing the maximum possible rank while keeping the number of parameters again the same. Right? So this is the proposed method, and let me show you some results. But before I go there, let me talk about the initialization of these frozen matrices. So as I mentioned, we initialize them using Gaussian random variables. And the main point here is that we want these to be orthogonal with high probability or full rank. We also tried like Gram-Schmidt initialization, where you initialize a big Gaussian matrix and then orthogonalize to get the columns of each of these heads. So this one also works pretty well, but there's not a huge difference between both of these initialization in terms of the experiments. So let me show you some results. So here the results are for this VIT model with 50 clients, and the number of trainable parameters is 2.4 million. So LoRa is applied to the attention matrices here. And what we are keeping constant across all of these rows is the number of trainable parameters. So although you can see the ranks being different, the number of parameters is the same across them. And the observation is that as compared to full fine-tuning, so this is like the best possible thing you can get because you're not using any low rank approximation here. All of the other methods are using low rank approximation. So we can come close to the full fine-tuning performance for non-IID data, whereas other methods kind of have a bigger gap with respect to the full fine-tuning performance. And one of the reasons why this is possible is because of those multiple heads and having a higher rank and more expressive update. Right. So these are the results for image data sets. There's also some results for language data, which have similar trends. So compared to the full fine-tuning, the proposed method Ravan comes close to it, closer to it, especially for non-IID data. Any questions?
One question, if I may go. So in every communication round, are you communicating all the parameters, or are you communicating just a compressed version of?
We are only communicating the LoRa parameters, which in this method would be all those H matrices.
No. I guess I'm just talking about the H matrix. I'm just trying to see how expensive the method is. Is it just in terms of the number of parameters, or is it in terms of the rank of the matrices you're communicating?
The communication cost will be the number of parameters, right? It will be proportional to the number. So you'll communicate all the parameters of those H matrices.
But I'm saying if the rank is lower, in one case, what people were doing, at most they had rank R, right?
Yeah. So over there also.
I'm just wondering whether they have an additional advantage because they have
okay.
something more compressible.
No, so that is why I'm keeping the number of trainable parameters the same for a fair comparison. So the communication cost remains the same as compared to previous methods.
What would be here the centralized baseline?
So centralized baseline.
Is the IID?
Yeah, no, it will actually be a little bit different from IID because like all of the data is in same place. Like, so that's not shown here. This would be full fine tuning with IID. Yeah.
Can you go back to the picture that the multi-head low rank summation? Like, I just have one quick question.
Sure, this one.
So like this, each rank is actually 2RD over H. So like why the maximum efficient rank is just a summation of that? All the rank?
It is a summation of, yeah.
Or like for example, if I have several matrices, all rank is less than R, all equal R. But like the summation of those matrices are not necessary to be the summation of all rank. So like,
Yeah.
I'm wondering how we can guarantee that the rank is higher, but the worst case is the rank is still the same.
Yeah. We cannot guarantee that. So that's true. Like that's why this is the maximum possible rank. The actual rank that you get really depends on what your data is and what these matrices are.
I feel like it's so interested in how we can like make the rank is maximum.
Right. Yeah. So no, this is just an upper bound on the rank. Yes.
Did you actually check what's the final rank that you get?
I think.
Maybe you need the
Right.
rank at some point during the fine tuning, but then it collapses again and you don't need it anymore.
Right, that's a good idea. I don't remember whether we checked it or not, but I'll keep that in mind. Maybe we can, yeah.
Also in the Gram-Schmidt, you're kind of doing the random features where the features are orthogonal. So you would expect rank to actually...
Yeah, it does increase. So in the final experiments, this is the method that we use for
You
initialization.
would expect H to probably not be the same subspace.
Yeah. So that's why, like, we expect the rank to be higher, but that's true. All right. Okay. So let me go on. Right, so these are some of the results which show close to full fine-tuning performance. And now you might be wondering, what is the number of heads that I should choose? How many should I have? So in general, adding more heads, like if you look at the expression for the rank that I had earlier, it would increase the rank if I add more heads. But the benefit saturates after a while, because the adding more heads gives an accuracy jump as long as the intrinsic dimension is more than the rank that I get, the maximum effective rank. But if the intrinsic dimension of delta W itself is smaller than this, then there's not much benefit of adding more heads. So here we are showing two examples with a lower parameter budget and a higher parameter budget. And this vertical line is that threshold where the intrinsic dimension, so this root NH is equal to D here. So we can see that up to that point, you get a better performance as you increase more heads. But beyond that, it kind of saturates. So there's some like optimal number of heads here, which should be like a hyperparameter that we need to tune. Okay. And finally, I want to also comment on the computational heterogeneity aspect. So here, one benefit of Ra1 is that because it has those multiple heads, in cases where there's computational heterogeneity, we can freeze some of them and only train a subset of them. So for a more constrained device, we can freeze more heads. For a less constrained device, we can just train all of the heads, and here we would train the first two heads. And only average those. So because all of these are averaged at the time of averaging, so the first head gets averaged across all the clients, and the second head and third head, and so on. So this gives some flexibility in terms of heterogeneity in the computation across clients. And you might think, oh, how do I select these heads? Like at each client, if I have 3 heads, which one should I train and which one should I freeze? So we tried some head selection strategies based on either just randomly choosing or looking at the magnitude of the weights and choosing it accordingly, or magnitude of gradients. And some of these give kind of similar performance in the experiments. But I think this is a topic that could have like further research exploring it. How do you select heads? Maybe train like a router to choose heads or something like that. So these are the experiments with computational heterogeneity. And yeah, so these are the previous methods that I mentioned. The het LoRa is the zero padding one. The purple one is the flex LoRa, which is the SVD one. So I think there was a question about that before. And then the green plots are Ra1 with computational heterogeneity. So here we simulated computational heterogeneity across devices using these kind of distributions. So this is like the fraction of clients that can train more heads versus the fraction of clients that can train less heads. And we observed that this method does well and is quite robust to computational heterogeneity. So with that, I want to summarize the first part of my talk, which is that this proposed method of multi-headed LoRa fine-tuning can address challenges such as inexact aggregation, computational heterogeneity, and insufficient rank. And I think there are still some interesting open questions. So I won't be there for the open questions session, but I can mention them here. One of the open questions is that these methods require the pre-trained model to be on the device to do the forward passes. So coming up with other ways to achieve this without having the pre-trained model would be quite interesting. One option is to do some black box fine-tuning where the pre-trained model is on the cloud and you're just making queries to it and then adding this module which is trained on device. Another interesting open question idea is to consider mixture of experts model and see how they can be trained in a federated setting. All right. So are there any questions before I proceed? I'll keep the second two parts shorter, more brief. So let's talk about the pre-inference. So what I mean here is that if you say have a pre-trained model W0 and all of these clients fully locally fine-tuned models without any communication with each other, and they get these models W1 to WM, then at inference time, what is a good way of combining these models? So this comes to model merging, which was also a topic discussed in some of the talks before. How do we merge these to get multitask capabilities of all of these clients and for efficient inference? So let me mention a couple of works related to this. So what Fed averaging does, Fed averaging is actually also a model merging method. It just takes a simple average of all of these locally trained models. So we can use one-shot Fed averaging, and it might work pretty well in some settings. So there's a whole literature on model merging, which was one of the most popular papers is this task arithmetic paper. And this is more related to multitask learning, where if you have a pre-trained model and then if you fine-tune it for many diverse tasks, then those fine-tuned models can be just averaged by just simply taking an average of these differences between the fine-tuned model and the original model, and those are called task vectors. And one of the reasons why these model merging methods work pretty well is because for the data sets that are considered here, the data sets are quite different. So if you look at the task vectors here, the cosine similarity between their vectors, this is a matrix showing it, they are quite orthogonal. They are almost orthogonal to each other. So because of that, just simple averaging works pretty well. But in a federated setting, the client's data distributions are not that different from each other. So if you just simple average, one-shot average the models, it likely won't work very well. And we can show that that is true using even like a simple quadratic example. So if you consider two quadratic functions, f1 and f2, that are shown here, and this is the average of those objective functions. And these are the local optimas, and this is the global optimal. Then we can see that W star, which is the global optimum, is not equal to the average of the local optima. And the simple reason behind this is that if you just take an average, you're not taking into account the curvature of these local objectives. So what we should be taking into account is the Hessians. So for quadratic functions, there's a closed form expression for the true global optimum, which is this, which is in terms of the Hessian matrices of the local objective functions. But this is for quadratic objectives. Can we extend this insight to design better merging or averaging methods for non-convex objectives? So if you have a non-convex objective, what do? One option is to consider a Taylor series expansion of this objective. So we can take each local objective and say we consider a second order Taylor series approximation around its local optimum. It would look something like this. Now, several of these terms can be 0 because Wi star is the local optimum. So the gradient is 0. And then the loss at Wi star is also approximately 0 for many common loss functions like the squared loss function or cross entropy loss function. So what we are left with is that we only have this term. So if we wanted to communicate this approximation back to the server, we would only have to send the local optimum and the Hessian matrix. And using these, we can reconstruct an approximate version of this local objective and then optimize the average of those local objectives. So this is the idea we are going to work with, that we are going to approximate the local objective and send this additional Hessian information back to the server. But the issue is that Hessians are expensive to compute and communicate. So it takes like order of d square operations to compute them. So a good approximation of the Hessians is the Fisher information matrix. So Fisher information matrix only requires first order gradients to compute, and it's a fairly good approximation. So this is a plot that shows similarity between Hessian and Fisher for MLP trained on CIFAR-10. It's adapted from that paper. Yeah.
So you don't need to compute the Hessian, right? You just need the Hessian vector product, if I understood correctly. So that you can compute with two backprops.
But you have to communicate it also.
But you can just, maybe if you go to a previous
Mhm.
can't you just communicate the Hessian vector product from each machine?
Hessian vector product,
So
like
you
which
just
one?
compute the HI W minus WI star and W minus WI star. Both are D bits and can be computed easily. And then I think there are like good PyTorch TensorFlow ways to also compute HVPs.
I see. Yeah, that might be an option. Let me think about.
You need it for any W.
Oh, yeah.
For any W.
But I thought, okay, I thought you would eventually do it for some Ws, but okay.
Yeah, that's true. So you'll have to do it for every W, because we want to reconstruct this function at the server. All right. So instead of the Hessian, what we propose is communicating this Fisher information matrix. So Fisher information matrix is easier to compute, but it is still D cross D. But there are good approximations of the Fisher, like some approximations like just the diagonal approximation or the K-FAC approximation, which are pretty efficient to compute and communicate. So using this idea, we proposed this algorithm called Fed-Fisher a couple of years ago, where we approximate these local objective functions using the Fisher information matrix, and then what we communicate is the WI star and the FI. And at the server, we can reconstruct the global objective function by taking an average of these approximate local objectives, and then to solve for the global W, you can just do gradient descent on this approximate global objective function to get the W star approximate.
So
Yeah.
to go back to my previous question, yes, you're right that you need to, if you do the Hessian vector product, you need it for every W, but you can solve this objective in a federated fashion by replacing Fi with Hi using Hessian vector product oracle calls to the clients, but we can discuss.
Okay, sounds good. Yeah, maybe it's like important to keep track of how many communications and computations you need for that. Yeah. All right. So some experiments, this is especially using pre-trained models, this method works pretty well. So we compared it with some baselines like OT Fusion, regmean, and dense, and just regular Fed averaging. And this is for ResNet pre-trained on ImageNet. This particular result has a small number of clients, but in the paper we have results with more clients, so this does generalize well to more clients. And we can see that this better way of averaging gives a pretty good 15 to 20% improvement as compared to the baselines, mainly because we are taking into account the curvature of these local objective functions around the optimum. Any questions about this before I go on? Yes.
I'm just curious, has this approach been applied to language domain problems? I'm just curious how, like, the Fisher approximation to Hessian, how domain.
I see. Yeah, that's an interesting. I need to check whether we did some experiments for language tasks. But one caveat here is that, like, with the academic compute, you could do this only for relatively small models, not for very big models. So we were kind of limited with that. All right. So next, I want to talk about another model merging related work where we try to merge models into a bigger size model. So what I'm doing here in Fed-Fisher and many of the model merging works also, what they do is you have models of the same size at all the clients and you average them, and the average model is also of the same size as each of the client models. But this kind of averaging does degrade the accuracy as you have more and more tasks or clients. So if you think about there being 5 tasks here, if you just store all of these task-specific models separately, it would be 5x of the cost of one model. If you average them, you get an average model which is just 1x of the size, but it does have an accuracy drop compared to keeping each model separately. So instead, what we propose is that you merge these models into a more flexibly sized model. So we don't merge all of these task-specific models directly, but we look at blocks of these models that are similar to each other. So these blocks can represent like transformer blocks or sets of layers of the model. And suppose I identify that like these two blocks are similar to each other, I can merge them while keeping the other blocks separate. So this is the method. It's pretty simple. Like what we do is just identify which blocks should be merged using cosine similarity as a measure of looking at the distance between blocks, and then greedily decide which blocks should we average next. And then how to merge them is done by any model merging method, such as just vanilla averaging or task arithmetic or other methods. Right. So then if you merge it to say a size of 2.5x, you'd get a model something like this. If I want to merge it further, some more blocks get averaged together to get an even smaller model. So the main thing is like you can flexibly control the size of the model that you merge into. Yeah.
So you still assume to start from the same initialization here, same pre-trained model?
Same pre-trained model for all the tasks, yeah.
But what is the eventual goal of all of this? It's like to get a model that works well across all tasks, or?
Yeah, the eventual goal is you get a model that works well for all the tasks, and it's efficient to store also.
It will be then a model that works well on average over these various tasks.
Yeah, yeah.
But it might be a model that is completely degraded for each one of the tasks.
So we do measure the accuracy for each task also, and then like take the average across the task. So each task would correspond to a path through this graph at the inference time. So at inference time, if you keep each task separately, it would just follow that colored path. Here, it would be one path following whichever blocks are merged. So like in terms of storage and memory at inference time, it is more efficient. But yeah, there could be an accuracy degradation. So obviously, if you're merging more, there will be some drop in accuracy. Right? Yeah.
Actually, here, if you have like enormous amount of tasks, like
Mhm.
like profiles and so on,
Mhm.
and every model is kind of sharing on these different data sets,
Mhm.
and you won't be able to store it on like one device. And then, like, how would you do that? Because like, let's say if you have 10 tasks, like, maybe you can store this flex merge like the last one, right? But if you have
Yeah.
2,000 tasks,
Uh-huh. Oh, I see.
it's just easier to do like a router that simulates like.
Yeah, that's true. I think that's definitely a possible option. If you have a large number of tasks, you might want to maybe cluster some tasks together and create several of these models that can be stored at different devices, and then use a router or something like that. So I think routing is a complementary or orthogonal way of addressing this. I think Marco also talked about this in his talk yesterday. Yes.
In the right diagram, yeah. There is no routing there?
There's no routing here.
It's a dense model.
So yeah, in this model, like if you look at the colors, each block, those denote the different tasks. So if I,
But if you do a forward pass, the information goes to all other blocks, so how?
no, so it would only go through those specific blocks.
So there is some routing.
There's some routing within this model. Yeah, that's true.
And how do you come up with this routing? How do you tune that? You do
So this routing is fixed for this case. So let's say if you are doing inference on the green color task, which is task D, you just follow the path of blocks that are green
so
here.
you need to know which task you're using.
Yeah, you need to know which task you're using. And then you just follow that path in this graph. And yeah. Right. So let me show you some plots of how this size of the merge model affects. So on the x-axis here, I have the deployed model size. And one extreme here is where you keep each task-specific model separately, no merging, which is this. And then if you do model merging into just a single model, that would be this end of the plot. And everything in between is where you have this flexibly sized model of different sizes. And what we observe is that, interestingly, so we do see this accuracy drop when you go from all separate models to model merging. But if you have a slightly bigger model, then you get a pretty big accuracy jump here. So having that additional size really helps improve the accuracy. Mm-hmm.
Just curious, is the rightmost side completely non-collaborative?
Yeah, so the rightmost side is where you have fine-tuned models for each task, and you just keep them separately.
So the 30 and the 8 are like completely different.
Yeah, so this is 30 tasks and this is 8 tasks, and you keep them separately. Mm-hmm. Right. So yeah, this is all I have to say about model merging. And I think I only have a few minutes left, but I'll briefly talk about one work related to efficient inference. So this is some very new work, and I actually have a whole line of work in my group related to efficient inference. I'm going to mention one that is most closest to federated learning here. So at inference time, now let's say you cannot fine-tune models on the edge or anything like that. You just have models that are trained and available in the cloud. And every time there is a query at a mobile device, you have to send it to the cloud. But we want to decide which model is the right one for this query. Because say if I have a really simple question, it need not go to the biggest and the most powerful model. If I have a math question, it should go to a math model. If I have a coding question, it should go to a coding model. So that's the idea here. And how do you train that router in a federated setting? Because each of these clients may have different budgets as well, because models have different costs. And how do you optimize this routing in using decentralized evaluation data? So the main motivation, as I said, comes from the fact that there are now so many different models available. So these are the company-specific ones, but there are lots of open source models. I think Hugging Face has hundreds of thousands of models at this point. And these models have various different accuracy and cost profiles. So this is the cost of different models per million tokens. So now that you have so many options available, when user queries come, these queries are also domain specific. They have different budgets. So it's not clear which is the winning model or the best model, especially if you're in a budget constraint setting. So what routing does is that it takes a query. So suppose I ask a question to ChatGPT or Gemini. My query passes through a sentence encoder, and you get an embedding of this query. So this is just like some vector representation of the query, because my query can be like a sentence of varying size. So instead, I'll just get a fixed vector representation. And there are standard sentence encoders that we can use off the shelf here. And then this query embedding gets fed into the router. The main job of the router is to estimate the accuracy and cost of a model M for that query. And there are many such models in the pool of available models. So if we get accuracy cost estimates for each model, then we can do routing based on some simple optimization. So you can select a model which has the maximum accuracy minus lambda cost, where lambda is some parameter that can be user specific. Right. So this is how a router looks like. The main thing, the challenging thing to get is these accuracy and cost estimates. And currently, there are many different routers that are proposed, but some commonly used ways of accuracy cost estimation is to use like a MLP-based router where you have a small model that is trained on these evaluations, or k-means clustering or nearest neighbors. But to train these routers, the thing to note is that what is the training data? The training data is pairs of query and model evaluations. So I have some queries, each query is evaluated on one or more models in the pool, and each such pair is scored by some either another LLM, or if it's just a math query, you know whether the answer is correct or wrong or something like that. So the issue is that we need a pretty diverse pool of these evaluations, and ideally for each query should be evaluated for all the models in the pool to get a good accuracy and cost estimates. And these can also evolve over time as more models get added, query distributions can change. Accuracy cost estimates can be tricky to find. And what makes it harder is that now a lot of these queries are generated on edge devices. So you might have clients with different tasks. So those circles represent 3 different clients, and the colors are different tasks on which models are evaluated. So if you have this kind of sparse and decentralized evaluation data, how can we train a router? So what we propose here is simply to take that router, which is the MLP router or k-means clustering, etc., and just train it in a federated manner. So it just applies plain federated learning to the router. So you have the central server, you have these clients. Each client will locally train its router, and then the central server will aggregate and average the routers to get a global router. And then once you have the global router, it can be used to choose the best model for each client. So once you have the accuracy cost estimates that this router gives, even if each client has a different budget, that lambda parameter, you can choose what is the best model for that client's queries. And this would change with every incoming query. So every incoming query will pass through this router, and you'll get those estimates. Okay. So I'll just show a couple of result plots. There are more in the paper. But what we observed based on these initial results, so this is done on router bench data, which is like a benchmark data set available for routers, and also another data set that my student collected on his own. Here, what we observe is that a global router, which is this solid, like a thicker line, that is the federated trained router. We are comparing it with client-specific routers that are only trained in isolation without any collaboration. So the takeaway here is that collaboration really helps in this setting because the evaluation data is so sparse and decentralized and also heterogeneous across the clients. And another surprising thing is, so this was evaluated on global test data, but what if you evaluate it on local test data? So the global router is evaluated on each client's local data. Surprisingly, the global router does well even on client's local data. Like you would think that a client-specific router would do well, but because these evaluations are really sparse, the data is quite limited at each client, and this collaboration helps a lot. So this is another method. So we are showing both MLP and k-means clustering results here. Right? So that's it. I want to conclude by saying that I think federated learning is still quite relevant in the generative AI era, and data and compute heterogeneity and resource constraints, privacy constraints are still important challenges that need to be addressed. Thank you. These are some of the links to the papers. Yes.
Just a question about why is still relevant. I would have imagined that this is the most relevant thing for this era now.
Why is it still okay? Because that federated learning, since it has been done for smaller or moderate size models, people think that with large models it's just not possible to do because they're just too big, right? So.
But in my view, okay, I'm just completely naive, but in my view, now that we have such large data sets, all distributed, this is the most relevant topic of this era. No?
Yeah, I agree. It seems, yeah, that's because I think the community has kind of has this impression that it's no longer that relevant because you have these models that are too large. Yeah, we have a broader view. I think this room is already convinced, so I don't think I need to convince people of the relevance of federated learning. Yeah.
I feel like for people who are not convinced, they say things like, "Oh, like current state of the art model
models are so good that you don't need to fine tune them on anything anymore.
Ah, interesting. Yeah, that might be one point.
And also that the only way to train this model is to centralize data and compute.
Yeah.
I think we completely miss on like lots of science and medical applications where these models are the large models are actually not good, and there is no way to get around decentralization. We often talk about like consumer technology applications, but there's lots of science applications where
Yeah, you could do with even smaller models. It's so very relevant in these applications. Yeah.
But I would have imagined that these large models themselves are trained in a federated way, no?
In the cloud, in somewhat, I think this is related to Zach's talks yesterday, where if you have different cloud data centers and a big model is trained using several different data centers, then yeah, it could be thought of as like a federated training as well. So that's where I think federated training, yeah.
Have multiple cores of a computer, I can imagine.
Yeah. So it's.
There's a mentality. But in other places that like everything you need to know is on the internet, and so an LLM trained on the internet should tell you everything. And not medical and other things, obviously counterexample, but that's not true.
All right.
Any more questions? Okay, yeah, if there are no more questions, we have a lunch break. We will come back at 1 p.m.